In this lesson, we're going to look at how scientists search for extraterrestrial life, alien life. The first aim is to compare the scale of key astronomical features, which is a lot easier than it sounds, then describe how we collect data on other planets and stars, and finally explain how scientists are searching for extraterrestrial life. So let's start off with a fun thought experiment. Imagine for a second that you're not yourself, but instead you are the playwright William Shakespeare. Now imagine it's the year 1600, making you 36 years old. In 16 years from now, you will die, but you don't know that yet. So let's imagine you wake up one morning and it's a lovely sunny day and you step outside. And a photon of light coming in from the sun strikes your nose, bounces off it, and reflects outwards towards space. Now, before we continue any further, just remember a few key facts. Remember that light travels at a speed of 300 million meters per second. So in 1 year, light travels just under 10 trillion kilometers. That's 10 with 12 zeros behind it. The distance that light travels in a year is called a light year. Now, the Earth has a diameter of 12,000 kilometers, so in a fraction of a second, that photon of light that bounced off your nose will have left the Earth, and it will start traveling outwards into space. So light has to travel 360,000 kilometers per second before it reaches our moon. But because light travels at 300,000 kilometers per second, it doesn't take very long to reach the moon. In fact, the light reflecting off Shakespeare's nose arrives at the moon in just over a second. But light continues on its merry way. So it goes on and continues until it passes another landmark in our solar system, one you should know very well, that being the Sun. Now the Sun is 150 million kilometers away from the Earth. That means it takes light 8 minutes to travel from Shakespeare's nose to the Sun. So hypothetically speaking, if you were living on the Sun, you would see Shakespeare's nose as it was 8 minutes ago. Shakespeare, in the meantime, would be 8 minutes older. But that is not where we're stopping. Light continues onwards. And now we're heading towards other parts of our solar system. Now, our solar system, that would be from Earth to Neptune, spans a distance of 4.3 billion kilometers, and it takes 4 light hours to cross it. So if you were living on Neptune and the light from Shakespeare's nose had just reached you, you would be seeing Shakespeare's nose as it was 4 hours ago. If Shakespeare had just developed a pimple on his nose, you wouldn't see it for another 4 hours. But this isn't our destination either. Let's carry on. Now we're going really long. And that's our next destination. This is Proxima Centauri, and it's the nearest star to us after our Sun. It's 47 trillion kilometers away, and that means it takes 4.7 light years for the light from Shakespeare's nose to reach Proxima Centauri. So if you're getting the hang of this by now, if you were living on Proxima Centauri, not that you could, it's a star, and you just received that light, you'd be seeing Shakespeare's nose as it was 4.7 years ago. In other words, by the time it's taken for that light to travel from Earth to Proxima Centauri, Shakespeare is now 4.7 years older. But this isn't our destination either. We're continuing on. So this is our galaxy, the Milky Way, and Proxima Centauri is just one of the billions of stars that make up our galaxy. We are located roughly around here. And because our galaxy is 1 billion kilometers in diameter, it would take light 100,000 years to cross it. So by the time Shakespeare's nose light leaves our galaxy, well, Shakespeare would have died about 99,084 years ago, because 100,000 years have passed since light first left our home planet. It's crazy to think that almost 100,000 years into the future, a civilization living at the edge of our galaxy would be seeing Earth as it was in Shakespearean times. This is why when you observe stars, you are quite literally observing history. So let's say light is now travelling from one galaxy, our galaxy, to the nearest next galaxy, which is the Andromeda galaxy. So let's zoom in here. So the Andromeda galaxy is 2,700 trillion kilometers away from Earth. That means it takes light an astonishing 2.7 million years to reach it. So by the time Shakespeare's nose light has reached Andromeda, not only Shakespeare has died, but you have died and everyone you know has died. And I'd add to that, every future ancestor that you could ever imagine has also probably died. But Andromeda is one galaxy in a sea of billions of galaxies that make up the visible universe, the part of the universe we can see. So the visible universe spans a distance of 45.7 billion light years away from Earth in any direction. So assuming the Earth is here, by the time the light reflecting off Shakespeare's nose has left Earth and spanned the entire visible universe, as well as Shakespeare dying and you dying, I'm afraid the Earth has also died along with the Sun, which would have exploded about 40 billion years ago. So a natural question is, what's beyond the visible universe and why can't we see it? Well, we're assuming space is infinite. That means it kind of goes on forever. So why are we limited? Why can't we see beyond this point? Well, the truth is, since the Big Bang, stars and galaxies beyond this point, the light coming from them has had to travel so far that there hasn't been enough time since the Big Bang for that light to reach us. So we simply can't see it yet. So in a previous tutorial I said I don't believe in ghosts, but I do believe in aliens. I mean, just think about it logically. Every one of these points of light is a galaxy, each with billions of stars, many of which contain planets. What are the chances that another planet would not have life on it? Very, very slim. But do I believe that aliens have visited our planet? No. I mean, you have to ask yourself, why is it always farmers in rural America that seem to spot aliens? If I was an intelligent life form and had travelled astronomical distances, I don't think I'd waste it on a farm in America. I think I'd maybe start with the Science Museum or maybe visit CERN and see the Hadron Collider, something like that. A farm just seems like a wasted trip. So here are the key things to remember from all this. Moons are the smallest of astronomical objects, providing and not counting in asteroids and comets, and they orbit planets. Next up, planets are bigger, and they orbit stars like our Sun. Remember that stars emit light, and if you look into the night sky and you see something twinkling, just like twinkle, twinkle, little star, that's a star. So starlight flickers, but if you're looking into the night sky and you see a solid sort of light, one which doesn't change, it's constantly beaming at you, that is a planet because they're much closer, so there's less interference between you and the light. But the key difference is, light is reflected off moons and planets so we can see them. So, in other words, light travels from stars and bounces off planets and bounces off moons so we can see them. Stars group together to make galaxies like our Milky Way, and galaxies group together to make the visible universe. And beyond that, we just don't know yet. So that's how we compare the scale of key astronomical features. So how do we know so much about our universe as it happens? I mean, we're stuck on Earth here, a tiny little fleck of dust in a sea of billions of galaxies. I mean, you've just got to pat yourself on the back as a human. It's amazing what we've achieved. Well, largely we know what we know about the universe by analysing the light that comes from galaxies and stars. The universe communicates with us using light, and we are now really beginning to understand that language. But there are other ways as well. We can send spacecrafts carrying probes that can be sent to planets and moons in our solar system. Probes carry instruments that continuously record data. For example, continuously monitoring temperature or soil acidity. This data is then sent back using radio signals. If you remember from the EM spectrum tutorial, we use radio signals for communication. Robots can be used as well, like the Mars rover. We can take photos using robots and collect soil and rock samples with the robot arm, which actually scoops it up for analysis. We've even recently sent such things to asteroids to collect rock samples from them. No matter what they collect, the data sent back using radio signals, scientists must still interpret the data. You see, different scientists could look at the data and read very different things from them, so the evidence is not always conclusive. For example, certain rock samples from Mars have shown tiny little bumps which look a bit like bacteria. Could that be evidence of life on Mars? Some scientists think it's worth investigating, whereas others think there could be a number of reasons for those rock patterns to be present. Obviously, telescopes have had a lot to do with our developing knowledge of the universe. Optical telescopes detect visible light. So in other words, they see what we see with our eyes, but closer up and in more detail. But remember, our eyes are severely limited. It only captures a small band of light coming in from the universe. We need other types of telescopes to help us see in more detail and get a better perspective. So radio telescopes, these giant looking things here, have been developed. They detect cosmic microwave background radiation, CMB radiation. This is radiation scientists believe that's left over after the Big Bang explosion. But I'll go into that in more detail in another lesson. Just so you value what radio telescopes have done, this is an optical image of a point in space, in fact of a nearby galaxy called Cygnus A. Doesn't look like anything special. But if you look at it under a radio telescope, suddenly you see a very different image. You see two lobes of intensely hot radiation. You see, you wouldn't feel too worried about journeying with a spacecraft into this region here, but if you saw it through this telescope, you'd know it means certain death. X-ray telescopes can detect high-temperature events, such as supernovas, when large stars explode, scattering their contents across space. Here is such an image. So a typical 6 mark on space could be around how has technological advancement helped us understand the universe better. Firstly, we've developed bigger telescopes. This gives us a better resolution image, more detail, like going from standard definition to high definition on your TVs. Bigger telescopes can collect more light to see faint stars and galaxies, and also they provide a better magnification so we can see further and discover new galaxies. Here is an example of an observatory which contains a big Earth telescope. Secondly, we've been able to observe how galaxies form and evolve. So the Hubble Space Telescope has taken images of galaxies at different stages in their life cycle. For example, from the nebula stage or to a red giant stage of a star towards the end of its life cycle, and then right at the end when a star explodes in a supernova. So it's helped us develop an understanding of star life cycles and galaxy life cycles. And of course, we can now use telescopes in conjunction with computers. You see, computers enhance telescope images to make them sharper and clearer. They can also store, like this supercomputer here, can store huge amounts of data for more effective analysis. And that is how we describe how we collect data on other planets and stars. So how do we actually search for extraterrestrial life, in other words, alien life on other planets? There's no way we can just send spacecraft after spacecraft into space with human passengers. For two main reasons. One, it'd be insanely expensive, and also humans have a very limited lifespan when you look at how far away other objects are in space. Well, firstly, what are we actually looking for? Well, one thing is we're looking for planets in a similar situation to our planet. Scientists refer to our planet as the Goldilocks planet. So if you remember the story of Goldilocks, for example, when she's eating porridge, one's too hot, one's too cold, and one's just right. Well, think of our planet as the just right porridge. It's exactly the right distance from the sun for life to exist. Any closer, it'd be too hot. Any further, it'd be too cold. Such planets are called exoplanets. And rather than sending crafts, we use telescopes. So SETI is a scientific project which stands for the Search for Extraterrestrial Intelligence. And it's been running for around 50 years now. Basically, we love communication, we use radio, TV, radar, so all this stuff is being sent into space, and hopefully intelligent aliens might be able to detect this someday. But what we're looking for are narrow bands of radio wavelengths coming to Earth from space. These would be the same narrow bands of radio waves that we use for communication. It's logical to assume that intelligent life on other planets would use a similar form of communication, so this is what we're looking for. These could have come, for example, from transmitters like we use. But 50 years have passed and we haven't got anything so far. But when you consider how big the universe is, it's not surprising really. Now we're also looking into detecting laser signals as well. And that's how we explain how scientists are searching for extraterrestrial intelligence.